Yes, so our first speaker today is John Sotiropoulos of Breker Verification Systems. He's based in Greece. He's a principal applications engineer with Breker, working on test suite synthesis and portable stimulus solutions. He has extensive verification experience in senior engineering roles at companies such as Intel, Facebook, and Draper Labs, and also worked for a number of years at Synopsys as a senior verification applications engineer. He has a keen interest in verification technologies and is well known as a UVM proponent and trainer. John holds an MSc in microelectronics and an MBA. As I say, he's based in Greece, but he's normally based in Boston. And the title of this talk today is RISC-V SoC Integration Verification, including systems coherency. Is your RISC-V SoC ready? Over to you, thanks, John.
Okay, thank you for the introduction. So good evening, everyone. Again, my name is John Sotiropoulos, and I will be going over the RISC-V Trek application that we have. The agenda for today is a brief introduction to the Breker technology, then introducing the core integrity tier of our Breker application, review the system integrity Breker app, which is the better known app that we have in the market, and then we'll summarize. So introduction to Breker technology. If we're looking at the verification and validation ecosystem, we'll start with constrained random UVM at the block or IP level, then we move to the full chip level. We do emulation or prototyping, and finally the post-silicon validation. So during this phase here, we call this the SoC integration, and there's certain things that we have to do when we're moving from the block IP level into full chip, and also when we go into prototyping. One of the things is we got to run end-to-end tests in the entire chip. This is where we try to reuse as much of your UVM environment as possible to save time. At the other end, when you're doing prototyping, you want to have firmware development starting early before you get silicon. However, there is also a number of tests and verification tasks that you need to complete during this phase. For example, your coherency, power management, connectivity, can you boot from all the devices? And one of the issues that we have today in the industry is that there's no best practices of what's the better platform to run some of those integrity tests. The second issue that we have is that those are some good tests that we're going to write. However, we cannot reuse them. We cannot reuse them in post-silicon, and it's actually hard to go backwards. We can take UVM components and UVM tests and pour them forwards to the full chip, but there is no this backward comparability that we can do. So all these tests here end up just being in a silo. So you can think of it as we have created some kind of wall between our SoC integration and all the other activities, the UVM and the post-silicon. And this is exactly what Breker is all about. Breker is all about breaking that wall down and be able to reuse your test between all the different platforms that you have. Now, how do we do this? You can think of it that this is analogous to the design synthesis, where you give your high-level language, your RTL, and you finally map it into a technology. The same thing can actually happen with your test suite or your test generation. If you define it at a high-level language, then we can map it. The Breker technology can actually take that high-level language and map it into different platforms, either your simulation or the prototyping, emulation, or silicon. Now, you're going to see some definitions here on the right. The AI planning algorithm, it's basically the way to generate smart stimulus, where you actually start from your goals and you work backwards to create the desired stimulus. The 3D coverage closure that we're talking about because we are defining actions and events at a higher level, you can think of it that we can also define a higher level coverage now, have certain scenarios be crossed together. And that's this synthesizable verification OS. This is Breker specific, of course, because you know, mapping to UVM or mapping to a simulation, we do need the hooks into those platforms. So we provide everything, and we can take tests again all the way from UVM to the silicon to the post-silicon production. So let me rate. Let me see here. So on top of the simulation, emulation, and prototyping, we can even go to a virtual prototyping. We can actually also generate code that will be exercised at the architectural level at a virtual platform. So if you're designing a RISC-V, you might fall into two different categories. You might be a processor developer where you're actually defining some simple core or some simple embedded processor that you're going to put in the design. Or you might be designing a big application processor or even a multi-core SoC. Now, the Breker app that we have, again, two different phases here. The core integrity, you can think of it as tests that will apply to a simple core that you're designing. And the system integrity, you can think of it as this is going to be the for the bigger multi-core SoCs that your processor might go into. So either way, we have core integrity tier and system integrity tier, depending on what you're designing. So this is exactly what I'm going to talk about next. And we're going to start with the core integrity. So as you can see here, taking the specification and assuming a single core, we can come up with a number of tests that will exercise some of the specification components and some of the rules that apply to RISC-V. We'll go over some of these in the presentation. At the same time, now that we have the privilege specification as well, we can do things as PNP, the memory protection, and we can also work with interrupt. So for those, we can also provide tests. But the way to look at this is that those become your core integrity tests here. This is the single core test that we can provide. So we can do a simple workload, okay? And think of the workload simply utilizing all the resources that the processor have to actually execute multiple movements of data in and out of memory. Page table, we have a predefined test where you can actually change your page table on the fly, reprogram it, and make sure that you have the correct response from the processor. We can work with interrupts. We can actually enable random interrupts during the execution of a workload or of multiple tests to make sure that the test still completes even though there's an interrupt in place. Of course, for this one, we are assuming that there's going to be a generic interrupt controller and the routines available for the interrupt handling. Modes and regions. This is, we're going to we can switch modes randomly while one of the workload tests is running between the different modes, a scene supervisor or user, and make sure that our test still completes. And then some memory order tests, and this has to do with putting fences around your instructions. So if you look at it as the results here, we provide the debug capability so you can see your workload actually running in real time. And as I said, this is a single core, and you have utilized 4 software threads inside. You can throw a number of tests in there, and it can show you exactly how your processor is going to schedule it and execute them. And you can also follow exactly the steps for each one of your tests or each one of your activities as it moves from thread to thread and become available to be executed. On the multi-core, we have we can take this single core now and imagine that you're putting this now in a multi-core environment. We also have the workload, and the this will become the multi-core mem order. For the multi-core mem orders, this simply means that we can create tests where actually two processors go after the same memory location and making sure that the correct order is maintained. And if you put this in our debugger, you can see now, for example, this is an example of 4 hearts here running 3 threads for each one of them. So you can, again, easily debug and visually inspect how a test is actually executed by utilizing all of your processor. Now, the beautiful thing about this is that you can also do a post-run analysis and make sure that the processor or the cores did not spend too much time on a single execution of the task. You can actually do some pretty good performance because you know that each one of the tasks that your program is broken down to, how long it's supposed to take. So you can actually see if something took much longer than you had expected. So this is all the apps that we give you, predefined tests that we provide. And we also allow for randomization. And when I say randomization, for example, you can define multiple memory regions, right? So we're not going to tie to a single memory or a single memory space, okay? You can give us your definition of your entire memory map, you know, what's cacheable, what are the different memory controllers, and all that. The different load store sizes. This is the way that you define which load stores you're supporting, and this also includes the atomic operations. So acquire, release, or the AMO. Memory allocation strategies is another thing that you can define. Do you want all your accesses to memory to be compact together? Do you want it to be spread out? Do you want to reuse same memory? And then, of course, the number of threads and the number of hearts that you have, which is also the load and store sources. So this was the tier, the core integrity tier that we went over. Now, the system integrity tier, you can imagine it that you're taking the core that you have designed and putting it into a bigger system, or maybe you're a systems integrator where you're taking the core from an IP provider and you're putting it into your system. So this is pretty much where we talked about. I know this graph might be overwhelming at first, but you can simply define your customizations. Then you can find an algorithm or a coherency and integrity test that you want to run. And of course, you can play this for the different instruction sets that are out there. Now, when I say that you can play this for the instruction sets that's out there, keep in mind, we don't just support RISC-V, we support all types of architectures. So in our case, this is going to be the RISC-V ISA here. So for the system integrity, where we have for single core scenarios, we have the test states and the transitions, where you actually look at your, depending on what your cache policy is, you look at the state diagram, and then you can actually draw sequences of transactions you need to do in order to cover all the cache states and all the transitions possible. Cross cache line boundary, that's an easy one. We make sure that we have some underlying cache accesses. And evictions, again, another easy one where we actually use algorithms so that we hit certain cache locations very, very often so that we cause evictions to occur. Now, taking that and putting it in the multi-core scenarios, we can produce cases where we have the cache line sharing, where this is one cache line being shared by multiple cores, and how this is going to be handled by the system. And this casline sharing actually can produce a lot of cases, because you got to think how many processors actually share the casline. You can have, depending on your casline size, you can have 3 or 4 different processors share the same casline. So you can understand that accessing that casline is going to introduce a lot of traffic. And also the false sharing, where you have half of your casline be utilized by one processor and half of the casline be utilized by another processor. So because of all of these, we can create a much more traffic dense scenario than the typical just randomized approach. And we can actually stress the workload to the max, as you can see, where the processor is fully utilized and you go in full speed. So to summarize, processors are, of course, hard to verify, right? So look at ARM and Intel, look at the number of years that they spend doing the verification of the processor. For RISC-V, we need to be able to verify fast. Automation is the answer. We can't take the approach that Intel and ARM use and all the investment that they've done there. We need to automate. We need to raise the level of abstraction here in order to create a lot more tests quicker. So RISC-V has special requirements in addition to that, like the custom instructions that you might be adding, different range of architectures that a company might define. Different processors, of course, have different needs, depending if you're talking about a small core or you're talking about an application processor. So what we find is this integration testing actually works well for both core developers and integrators. So as a summary, the next step, again, Breker has been around for a long time, and we've been part of the verification ecosystem for x86 and ARM. Breker is also becoming part of the verification ecosystem for the RISC-V, and we're already working with both developers and integrators on RISC-V designs. So there's also a belief that we have that RISC-V has a lot of room to grow. And what I mean by that is that the designs nowadays are on the smaller side, on a single core. We don't have that many multi-cores, multi-clusters. So because we've been there through the evolution of x86 and ARM architecture, we know what's coming for RISC-V and all the verification challenges when RISC-V becomes successful. So this is it. I think I kept under 20 minutes. Okay, perfect.
Yeah,
and 1 minute
perfect
for questions.
Yeah, that's perfect timing. Thank you, John. Yeah, we do have one question actually. So if somebody was going to add their own instructions to the RISC-V processor, could they still use Breker in that new RISC-V SoC?
Yes, because I mean, what we do is the generation of the stimulus. So yes, you can take the additional instructions that you add and generate a stimulus. Of course, it has to be a collaboration at that point so that we can add that instruction and how that instruction is going to play out. But yes, we do have support for custom instructions.
And do you take a standard format for adding those new instructions in?
I'm sorry?
Do you use a standard format?
Oh, a standard format.
For adding those instructions?
Yeah. So I'm not sure if we have a best practices or if we have the flow already defined. That's something that I can get back to you with.
Okay.
Yeah. Good question, though.
Okay. Thank you, John.
Okay. Thank you very much, guys.